The next topic is dimensions of physical quantities. Let us consider the derived quantity velocity. You know that velocity is displacement divided by time. Now what we do, in place of velocity we write v, in place of displacement we write L, and in place of time we write t. Now note that velocity has many different units. You can express the velocity of a moving object in kilometer per second or in meter per second, in miles per hour, kilometer per hour. Many different ways are there of expressing velocity. That means there are many different units. But in all those units, we are basically dividing a length by time. So that fact is captured here. Or even more accurately, this equation shows how the derived quantity velocity depends on the base quantities length and time. It is that relation. So which of course we can also write like this, LT inverse. So this LT inverse is called the dimension of the derived quantity velocity. It tells us how the quantity V is derived from the base quantities length and time. But we do not simply write an equation like this, because one may confuse this as an ordinary equation. Instead, James Clerk Maxwell suggested that we use square brackets whenever we are talking about dimensions. So the meaning of this equation is that this is the dimension of the quantity velocity, which is this. So it tells us how velocity is related to the base quantities length and time. How many base quantities are there? 7 base quantities are there. Length, time, mass, electric current, thermodynamic temperature, amount of substance, and luminous intensity. So you may notice one thing, that the quantity velocity, although it depends on length and time, and that's why it's a derived quantity, actually does not depend on mass, nor does it depend on the other base quantities. It does not depend on luminous intensity or amount of substance or thermodynamic temperature. So that is why you do not see any other symbol here. Actually the other symbols are there, but you cannot see them. If I write the other symbols, then this equation will look like this, which looks quite complicated. You do see that, but before I say what this is in its entirety, M stands for mass. L and T you already know. L stands for length, T for time. A denotes electric current. K is thermodynamic temperature. CD is luminous intensity. And MOL is, it represents mole, amount of substance. So you see here all the basic 7 quantities: mass, length, time, electric current, thermodynamic temperature, luminous intensity, amount of substance. Now you can interpret this equation like this. First of all, how do you read this equation? You read it like this: the dimension of velocity is this expression, not these exponents, okay? This entire expression is the dimension of the derived quantity velocity. In this expression, the contribution of length is 1, the contribution of time is -1, and the contributions of the other base units are all 0. They do not influence velocity in any way, and that is why all the units of velocity that you see, kilometer per second, meter per second, all possible units have only a unit of length and a unit of time, kilometer per hour, meter per second. You do not see kilogram meter per second. Okay, you do not see things like that. Or say meter per second times Kelvin. No, it only depends on length and time. So let us now see the dimensions of actually the base quantities first, because it is in terms of the base quantities that we have derived quantities. So just like a derived quantity has a dimension, base quantities themselves also have dimensions. So let us see that next. So these are the 7 base quantities and their dimensions. The dimension of length is capital L within square brackets. You may also see that there is another notation, that ordinary capital L without any square brackets. I am coming to that later, okay. That is also used elsewhere. We are not going to use that notation. Mass has dimension m within square brackets, or someone can simply write capital M. Time has dimension capital T within square brackets, or one can write simply capital T. Electric current has dimension capital A within square brackets. In that other notation, they write I, capital I. Thermodynamic temperature, we denote its dimension by capital K within square brackets. In that other notation, they denote it by theta, capital theta. Normally the theta that we write, that is small theta, this is capital theta. We denote the dimension of luminous intensity by Ct within square brackets. They denote it by J, and the dimension of the amount of substance for us is mole within square brackets. For them it's capital N. And this same equation, in their notation they would write like this. They do not use square brackets. Instead, for dimension they simply write dim. Dim of V means dimension of the quantity velocity, and that is this. The meaning is same, but the notations are different. We won't follow these notations, okay. We are going to follow the square bracket notation. Normally we do not write such a cumbersome expression, and especially when other quantities do not have any role to play in the dimension of the quantity that you are considering. However, still sometimes we omit this part and keep M. Okay, M, L and T we keep in places where mass becomes important. In velocity, mass has no role to play in this context, but elsewhere you will have mass playing some role. For example, mass plays a role in the quantity momentum. Mass plays a role in the quantity mass itself. Mass plays a role in the quantity force. So if we are considering physical quantities which in one way or another involve mass, length and time, then we do show M, L and T, even if one or more of them actually have no role to play in that quantity. Alright, so what comes next? So next we consider a general physical quantity. Say Q is any physical quantity, then its dimension will look like that. In our notation it looks like this, where these exponents A, B, C, D, E, F and G can be any exponents. These are numbers after all, and in their notation that same dimension of Q will look like this. And these exponents show how Q is related to the 7 base quantities. Now let us next see some actual physical quantities, derived quantities and their dimensions. Based on which base quantities are involved in giving you the derived quantity in some way, there is a small classification of physical quantities. The first type is geometric quantity. I say first type, but there is no first or second. A geometric quantity is a quantity which depends only on length, only on the base quantity length. For example, volume is a physical quantity which is a geometric quantity, because a volume, no matter what type of volume you are considering, for example, you may consider the volume of a parallelepiped, then you have to multiply length, breadth and height, but all these three are ultimately just lengths. So the relation between volume and length in that sense is this: volume is simply the cube of length, and as such the dimension of volume is this L3. But if you also want to include in this notation mass and time, then you write like this: M0 L3 T0, which shows that mass and time have no role to play in the quantity volume. Next we have physical quantities, which are kinematic quantities, which are about motion but not taking into account the cause of motion. Cause of motion, of course, is force. So here mass is not involved, but length and time are involved. One kinematic quantity we have already seen, which is velocity, and its dimension is this. So where mass actually does not contribute anything, but length contributes 1, time contributes -1. And another one is acceleration. Here mass again contributes nothing, length contributes 1, time contributes -2. And then we have another type of physical quantities. And that next type is dynamic quantities. Quantities where mass also plays a role. Mass, length and time, all of them play their roles. For example, force. Force has this dimension. You do understand how it is coming, right? You can view it as mass times acceleration, or you can actually use the more accurate definition of force, that it is the rate of change of momentum. Momentum is mass times velocity. Mass has dimension m, velocity has dimension L times t minus 1 or t to the power minus 1. But it's rate of change of that. That means we are again dividing by time. So that way you get t to the power minus 2. Another dynamic quantity would be momentum itself, mass times velocity, torque. These are all dynamic quantities. But there are some quantities which, although if you measure them you will get a number, but you won't get any unit. They are called dimensionless quantities. A dimensionless quantity is angle, for example. I should perhaps make it more clear, my statement that I made just now, that such quantities do not have units. You would object, you would say that angle has unit, for example 2 radian. So by not having unit, what I meant is that the radian unit does not depend on the 7 fundamental units or 7 base units, or 7 base quantities rather I should say. If you recall the definition of radian, what is it? You just put the angle so that its vertex coincides with the center of a unit circle, and then you see what arc the angle subtends on the circle. You measure the length of the arc and then you divide that length by the radius of the circle. Whatever number you are getting, that would be the radian measure of the angle. So actually you are dividing length by length. So that's why you do not get any contribution from the 7 base units. In that sense, angle is dimensionless. In the universe where the 7 base units are creating all the quantities, or rather I should say 7 base quantities are creating the other derived quantities. In that universe, angle is dimensionless in the sense that it does not depend on these 7 base quantities. None of them contributes anything to angle in that sense. But of course, there are other quantities which do not fall under this classification. For example, this next one, density, for example. Density is mass divided by volume. So its dimension is this, m1 L minus 3, or m to the power 1 L to the power minus 3. It is not a geometric quantity because it does not depend only on length. It is also not a kinematic quantity because time is missing. It's not a dynamic quantity either because again time is missing, and it's also not a dimensionless quantity because m and L do contribute something, not 0. So you will encounter many other such quantities which are none of these. Now, are these dimensions of physical quantities going to do anything for us, or is it merely just an observation, a curiosity? We will see that we can use these dimensions to check the correctness of some physical equations in a particular sense, but that we will do next week. So see you next week with those things. Until then, this is me, Lucifer, from a mathematical room. Have a nice day.